Okay, good morning everyone, guys. Here we are ready to... I can't see you yet. I guess you can see me now. Anyhow, being 4 o'clock, we are going to start soon our first academy, fluorseals Academy. The today topic will be manufacturing process, mainly for PTFE, but we will see something also about PEEK and other fluoropolymers. Of course, this is an introduction webinar. We will have many other webinars in coming months, and we will go through different materials, different application of PTFE, and also some features, some interesting stuff that we will let you know soon. I guess it's 4.1. We can start right now. I hope that you are all there, and for any people that would like, we will send you the record of this webinar so that you can show it to your colleagues or you can just see it again if you have any doubts about it. Okay, PTFE is a thermoplastic material, but not like other thermoplastic material, it is not melt processable. So this means that it cannot be produced by screw extrusion or injection molding. This is pretty unique for a thermoplastic material, and so how we do produce semi-finish and finished parts made of PTFE. There are two main technologies for granular PTFE, and we are talking about ram extrusion and compression molding. Ram extrusion is the only continuous technology that we know, and compression molding allow us to produce semi-finish tubes and rods plates also. Besides of this technology, we do have also capabilities for isostatic molding, that is a kind of compression molding that we will later see which are the differences between normal compression molding. Also, skiving and etching are two technologies that allow us to produce, in the case of skiving, plates and films out of a compression molded billet. Etching is the technology that allows PTFE to be gluable, because PTFE has a very unique properties that is not gluable as it is, or it's challenged to glue. By using etching technologies, this allows PTFE to be gluable. In the production, in the manufacturing of finished parts, we do have capabilities of machining by turning, milling, punching. Welding also is a way that allows us to produce finished parts, thermoforming and dimpling. Talking about ram extrusion. Ram extrusion is the only continuous technology to produce a continuous length of a tube or a rod made of PTFE. This technology is quite easy, but also challenging. As you can see in the picture on the right of the screen, this is a drawing of how an extruder is made. But before seeing the technology itself, let's talk about the process steps. So the first things that we have to do is to select the right resin, because the resin that can be produced by ram extrusion, it is a free flow material or a pre-sinter resin. We will see in the next webinar the difference between resins, free flow, what does it mean, pre-sinter. But just take in your mind that on ram extrusion, we can use only free flow resin. In rare case, it's quite challenging, but it can be used. But the 95% of the application using a ram extruded product, the selection of the resin must be a pre-sinter resin. After selecting the right resin, we do have to condition the resin itself, because the temperature that the resin has during the process allow us to have a better property, better processability of the material. So it's really important, the conditioning of the resin. After that, we go really on the machine. We have to load the hopper. So on the top part of the extruder is not showing this drawing. There is a tank that is storing the powder. After that, there is a vibration ramp that allows us to fill the mold, so the die cavity filling. After this process, a ram, so we have the powder inside the mold, let's say, and there is a ram that is going to compact the powder. Once the powder that we have filled the mold has been compacted, we have what we will call from now on a charge. The ram will open again and we will fill the mold with some more resin. The ram goes down and we will have a second charge. This second charge will push the first charge, the previous charge, down inside the extruder. So charge after charge, the first charge starts to get in contact with the sintering areas. We can see in the drawing the heaters bands. So basically we have mold, powder, it start the compaction, the powder start going down, and the sintering areas and the materials start to be sintered. After the sintering, of course, it's really important also the cooling, because the cooling is what gave stress that might lead to a stress, internal stress of the material, the properties itself, and we can talk about this in the next meeting. The cooling is really important to allow us to have an amorphous or a crystalline material. This leads to different properties, but I don't have to push too much. We will see shortly. Okay, now we can see something deeper about what we have just discussed. On the bottom part of the picture, we can see what I explained you previously about the charge. So we have a first charge, a second charge. Once the ram goes down, the charges start flowing inside the mold, and we start having material inside the sintering area. This is really important because, as you can see in the left part of the picture, the first circle, white circle, is the material, is the charge itself. But once it starts going into the sintering area, we see in the circle some black parts. That's the first material that gets to the sintering temperature. As you can see, going down into the extruder, we have a sintering that is going through all the material, so that we can have a very good sintered material with perfect properties. But then what we see on the last circle, it becomes smaller because the material, when it's cooling, also undergoes a shrinkage. In this step, it's really important to control the temperature to allow the less possible stress inside the material, because the shrinkage and the temperature itself will lead to stress. It's really important for the machining to have an extruded bar or tube with less possible strength. Of course, our process, our know-how is to have an extruded bar or tube with less possible stress. And when it's not enough, what we can do? We can undergo the material to a extra annealing. The annealing is a post-process to the extruded bar that allow to reduce the stress inside the bar, but this is needed only in certain cases where you have to keep very strict tolerances in the machining, and it must be evaluated because, of course, being an extra process, it's an extra cost, it's also complex, and it's not always needed. Because, as we explained before, we do have a way of extruding that allow us to have a very stress-relieved materials also after the extrusion. Which are the sizes that we are able to produce? We can produce rods from 4 millimeters, OD 4 millimeters, up to 160 millimeters, and tubes that goes from an OD of 10 millimeters up to 150 millimeters in OD with variable wall thicknesses. Of course, we have a very wide tool portfolio, so we can vary the wall thickness of the tubes in many ways. I guess that many of you already know. Okay, in the picture, what we can see on the left side picture, we see the top part of an extruder, so where the powder is filling into the mold itself, and also the heating area. In the right picture, sorry, we see the end of the end of cooling and the bars that are coming out from the extruders that are ready to be cut and for the next step of the process. Next technology is compression molding. So we have said that ram extrusion is a continuous process, allow us to produce rod and tubes in variable length, but we can't produce any plates. By compression molding, we have the ability of producing rods, tubes, but also plates. The technology is completely different from ram extrusion. So how does it work? It works mainly, we have a mold that has to be filled with powder, applying a pressure by a ram. We compact the powder and we have a green shape. It's just compacted powder. Of course, it's better to see also the process steps for compression molding. As we have seen before from ram extrusion, only certain type of resin can be used for ram extrusion. That's the same for compression molding. For example, pre-sinter resin that we have mentioned before from ram extrusion, it can be used for compression molding, but we do have the ability of molding free flow resin and non-free flow resin. After that, also the conditioning, like for ram extrusion, is a really important step for compression molding. The temperature at which the PTFE is molded can lead to scrapped cracks inside the material. So this is a very important step to control the temperature, the resin temperature before the molding. After conditioning the powder, the mold must be filled. So we have to fill the mold with powder, applying a pressure so we can consolidate and compact the powder into the green shape. We have to remove this green shape compacted powder and place it inside an oven where it will undergo what is called sintering cycle. In the sintering cycle, one of the most important steps is the cooling. Okay, here we can see deeply what is happening during the preforming, so the powder compaction and the sintering. As you can see in the picture, we have powder that has a very high volume, and applying a pressure, it reduces its volume, so the grain of the powder start compacting and removing the air between particles. As soon as we remove the pressure, we have a compacted powder that will undergo immediately an elastic recovery. But a very important step again is to rest this green shape for a certain amount of time, because PTFE will undergo a delayed recovery. So this means that the particle has to release the stress accumulated during the compaction, and also the air that was trapped inside has to flow outside the green shape. After these 4 steps, we will place the green shape inside an oven, where the green shape will undergo the sintering cycle. The sintering cycle, what happens to the PTFE? PTFE starts to be heated up, so it will expand because of thermal expansion. Also, it will release some of the stress that was accumulated during the compaction. Once it reaches the sintering temperature, all the powder melts. This means that we melt all the crystalline parts of PTFE, and this allows us to create a strength between particles because they are fusing together. Really important step is the cooling. We have mentioned before that the cooling can affect some properties, but also allow us to eliminate any porosity or voids inside the material, because we have the material that fuses together, and during the cooling, it will start shrinking, and so all the air or voids trapped inside will be pushed outside of the PTFE shape. This is a typical sintering cycle for a 150 millimeter wall thickness tubes. As you can see, it it lasts almost 80 hours, almost 4 days of sintering for a 150 millimeter shape. We can see a first part of the graph that is the heating up of the material, where there is 20 hours to heat up the material at a temperature around 350 degrees. Then we have a plateau that's really important to stabilize the temperature of the material before the melting. And we have another plateau, 12 hours again, to reach a complete fusion of the material. After that, it starts the cooling. The cooling is probably one of the most important part of the sintering. Why? For two reasons. During the cooling, we have mentioned that we are eliminating any porosity, any voids, but we are going to influence a lot of properties of the material. In the next slide, we will see how. Again, we will have another plateau for stabilize the temperature before the crystallization. So we are above the melting temperature, we melt all the crystalline. Now we have to create again this crystalline that gives strength and properties to our material. So it's really important that we control. We have an even temperature in all the material, and we can start crystallization. All the material is the same temperature. We will have same crystalline all over the material. That leads to a very good mechanical and, generally speaking, PTFE properties. Also 10 hours to cool down to a temperature that allow us to handle the material and to go to the next production step. We mentioned several times about, okay, with the cooling, we can influence the properties. With the preform pressure, like is shown in this graph, and now we are going to see any details of this graph. So basically, it's really important that a lot of manufacturing steps can influence the properties of PTFE. It's really important for all of us to know the exact application of our product, because changing these manufacturing parameters, we can modify the properties of the shape of the seals of the insulators that we are going to produce. This will allow us to give a better product, a more performing product to our customer. So let's see what the graph is showing us. Basically, we have on the lower axis the preform pressure. The preform pressure, in this case, we will take three examples: 10, 20, and 35 as a number of preform pressure. We are talking about newtons on square millimeters, that's the same of megapascal, but let's take an example, 10, 20, and 35. If we are molding our shape at 10 megapascal, we will see these lines for the elongation, the gray line. We will have a quite good elongation. At tensile strength, the light pink line, acceptable tensile strength, but going to the dark pink line, we see that the dielectric strength, it's not the best. As soon as we mold the same material at a higher pressure, and we assume 20 megapascal, we can see that the elongation has dropped a bit comparing to when we molded at 10, but the tensile strength become higher, and the dielectric strength is almost the best dielectric strength that we can get from that PTFE material. Going up to 35, we see that the mechanical properties, tensile strength and elongation, dropped a bit comparing to 20, but again, the dielectric strength has been reduced. So this shows us how changing the preform pressure, just one manufacturing parameters, allow us to have different properties, different material properties. Before we mentioned cooling is the same things. If we are going to cool the material at a certain speed rate, very fast or very slow, we will have a different crystallinity inside the material, and this will lead to a material that is more elastic or more rigid. So for example, if we do have to produce a seal that has to be elastic, because during the mounting of the seals itself, it will be modified. So we need a material that has a very good elastic yield. We want a more amorphous material. We will fasten the cooling. If we want an electrical insulator, we know that with a better crystalline structure, so a slower cooling, we will have a better dielectric strength. And these are the same PTFE raw material, but producing using different manufacturing parameters lead to not completely different, but leads to differences inside the properties of the material. And that's really important for all of us, knowing which is the application, because it will allow to give to our customer a better product. Going to compression molding portfolio, we have a very wide portfolio range. We can mold rods up to 770 millimeters, tubes up to 3 meters in OD. So with different wall thicknesses, but we do have abilities of mold tubes, PTFE tubes up to 3 meters in OD, and plates. Here you can see some standard size of plates. Of course, we as fluorseals, we are always open to evaluate a new project where it might need a new tool. Don't be afraid of asking, oh, shall we think about a new tool because I have this project or this other project? Because if it's interesting, we always are happy about doing new tools to win new business and new project together with you guys. Okay, this is a kind of evolution of compression molding, because isostatic molding is exactly the same technologies of compression molding, but the way the pressure is applied to the material is different. In compression molding, we have an axial the pressure is applied only on one axis. So we have RAM that is going to compress the material in one direction. Bi-isostatic molding means that the pressure will be applied on the PTFE all over, on all the direction 3D. Which are the difference between a compression molded material or an isostatic molded material? There are a couple of differences. First one, probably the more difficult to understand, is that isostatic molding material is an isotropic material. PTFE, when it's molded by normal regular compression molding, it is an anisotropic material, so that means that the properties, mechanical properties, for example, has some differences between if they are tested in the cross direction to the molding direction or in the molding direction. So we have a shape of PTFE that has slightly different properties in the direction where the properties are studied. With isostatic molding, of course, applying the pressure all over the material, we don't have this orientation of the properties, let's say. Also, by isostatic molding, we do have a more compact structure because, and this is seen also by the next properties, a lower porosity. Because applying the pressure all over the shape allow the PTFE to receive the pressure in a better way. So the porosity will be less. This porosity is not something that will help in the permeability, but for example, as we will later see, can help us having a better surface roughness inside an isostatic molded material. Also, the stress, the internal stress is less. As we have just explained, we have an anisotropic material with regular compression molding because we have a difference between the direction we do test properties. This means that we have a kind of stress inside the material. With isostatic molding, we are able to have a more homogeneous stress all over the material. Another interesting things of isostatic molding is that allow us to produce a thinner wall thickness tubes. Of course, isostatic molding is kind of a niche comparing to the compression molding. And why we are saying only special compounds? Because we do really use isostatic molding in certain cases, only when it's really needed by the application. When certain properties, certain features required by the customer can be reached only using isostatic molding, so it makes sense because isostatic molding is very nice, but it has also a lot of scrap, some problem in in the way it is produced, so the cost is quite higher than regular compression molded material. Now we can see which is the main difference between compression and regular. We have seen before that in compression molded material, only one axis. Here we see the white arrows inside the picture. Those arrows are the pressure itself. So in which direction the pressure is applied, in this case is from internal to external pressure, is applied all over the PTFE powder. The process steps are almost the same that we use for compression molding. So we have to select the right resin, we have to condition at the right temperature the resin. Of course, the mold must be loaded with this resin because then we will have to compact into a green shape, and removing the green shape from the isostatic press, we can the green shape can undergo the sintering and the cooling, so on. Okay, again, which is the difference? Normal compression molding, the pressure is applied in one direction. Isostatic molding, the pressure is applied all over the shape. I mentioned before about the surface roughness. Here we can see the proof of the statement I made before. As you can see, the first two pictures, we're talking about regular PTFE. The first picture is made on a compression molded material. The second one is made on isostatic. Come no? They told me that you can't see this picture, unfortunately, but mainly we will share it with you, this slide, so that maybe you can remember about. And what is showing is a microscope picture of a compression molded and isostatic molded material, and we see a better surface roughness, less holes, let's say, inside the microscope picture from the material that is molded by isostatic molding. Capabilities: fluorseals has capability to mold the tubes by isostatic molding up to 125 millimeter. So we are talking about seals usually, because as we mentioned before, so the wall thickness can be controlled, and the properties itself that are generated by isostatic molding fits a lot the seals application. Now we will have a break from PTFE manufacturing process, and we will see the technology that we as fluorseals developed for melt processable polymers like PEEK and other fluoropolymers that are melt processable like PFA, PCTFE, ETFE, and other fluoromelts. Basically, we started with compression molding melts polymer because of our know-how came from PTFE, but we realized that compression molded shape had some problem. So thinking about how we can solve this problem, our engineers come out with this idea about rotomolding. Rotomolding is a technology that fits molding of tubes, thin wall tubes, from 4 inches, from 100 millimeter in OD up to 500 millimeter now, but who knows, maybe soon also bigger. This technology is mainly the word itself, it's explaining a rotomolding, so it's a molding by a centrifugal force. This technology is really competitive comparing to compression molded items, because we know that for thermoplastic material, we have injection molding that is really cost competitive on smaller size, smaller than 200-300 millimeters. But when we are going to size bigger than 100 millimeters, up to 500 and also more on this kind of material like PEEK, PFA, PCTFE, we do found on the market a lot of compression molded material. But compression molded material adds some weaknesses. For example, the mechanical properties are good, but they are not good enough. the strength, the hardness of the material is high, is even too high for certain applications. So by this technology, spin-cast technology, we were able to solve this problem for the industry. And now we do have a very good market of this product, spin-molded product, that has incredible mechanical properties, almost the same of injection molded items, but with some differences. The flexibility of the size are really interesting, because when we are talking about injection molding, we do always have to produce a new mold. With this technology, we have a flexibility on size. The wall thickness can be varied super easy. The consistency over time is incredible, is again comparable to injection molding, but we can go to a bigger size quite easily, and mainly we compete against compression molding material. So when it comes to spin cast technology, it's a very good technology that allows us to produce similar material to injection molding, but that has to be competitive with compression molding, and we win this competition. So we can't share too much details about this technology because, of course, it's a proprietary technology. But what we wanted to share with you is that these products, this technology for melt-processable polymers in form of tubes is incredible. And we are always open if you have any inquiries or any questions about the properties of the material, to share with you information about and comparable with other with the same material processed with different technologies. Okay, now we can go back to PTFE. Before we mentioned that the two main technologies to produce semi-finished shape made out of PTFE are compression molding and ram extrusion. Of course, there are some post-process that allow us to produce, in this case, when we're talking about skiving, films and plates. A compression molded billet tube is a very big tube, around 700 kilos, will undergo this skiving. This skiving is almost, this is an example that my colleagues always like when I do it. It's like peeling an apple. Basically, we have a blade that is going to remove the peel, the apple, it's like peeling an apple again, sorry. So we have a blade that is fixed. We have a rotating cylinder that goes inside the blade, and the film will come off the blade. This technology allows us to produce films from 1 mil, that means 25 micron, up to 6 millimeters. But when we are talking about films, we always stay below 1 millimeters, below 0.1 millimeters, and we do have the abilities of producing film from 25 micron up to any thickness you need, and we don't need any tool, anything, just to have 25 micron or 29 micron. That's up to our customer application or our customer needs. Also, as I mentioned, it's quite useful to produce plates. In this case, plates by skiving can be skived up to 6 millimeters, and in the maximum width of 1,500 millimeter by 1,500 millimeter. After this skiving, another post-processing that can be done on PTFE, it's called etching. Etching is the only way known to make PTFE gluable. What does it mean? PTFE has a certain surface energy that doesn't allow anything to attack its structure and to glue to the PTFE. But using this etching, that can be sodium ammonia etching or sodio-naphthalene etching or sodium ammonia etching, this allows us to remove a layer, a fluorine layer from PTFE. And as you can see, the PTFE will become black because the carbon of the molecular structure of PTFE will be shown. The carbon is alike to make bonds with other stuff like glues. And so the surface of the PTFE can be glued with other surface like metal surface or whatever. This is, as I mentioned, a post-process. We can share with you some information about how to glue PTFE and which is the differences between sodium ammonia and sodium naphthalene. So if you are interested about, do not hesitate, just ask to us. Okay, so now we have seen how we, as fluorseals, can produce semi-finish items. We have seen from extrusion, compression molding, isostatic molding, skiving, and etching. But now we do have a semi-finish. We do also have to produce finished parts. As we mentioned before, PTFE is not a melt processable polymer, so we cannot do any injection molding. So injection molding is a technology that allows to produce finished part directly from a resin. With PTFE, this is not feasible. We do always have to produce a semi-finished shape. After that, it must be machined. The machining can be just machining, lathe by a lathe, milling, but also some grinding. The two main technology are lathe and mills. Of course, as fluorseals, we do have a very wide machine portfolio. We have abilities up to 5 axes in continuous. We do have a lot of machine that fits the application, the finished part shape itself, to be really competitive in producing that, from simple flat rings up to very complex part that must be produced using a 5 continuous axis machine. Some of the most common shape are like envelope gasket, ball valve seats, butterfly valve, O-ring, bellows. But all these parts made out of PTFE will be explained with more details in the next coming webinars, where we will see application of the PTFE. So we will share with you some finished parts and its application inside the industry. I thought it was finished, but we have one last slide. So basically, these are the number of machines that we do have in different plants. We have 50 almost more than 50 automatic lathes. These automatic lathes are lathes that are really fast in producing easy shapes. Then we do have more than 120 CNC lathes and milling. These machines are kind of slower comparing to automatic lathes, but allow us to keep a stricter tolerance, more complex shapes. So as you see, we have a wide ability of choosing the right machine for the right parts to get you a very good competitive price, but also the best quality possible. I want to thank you all, guys. If you have any question, do not hesitate to chat us, and I give you kind of 10 minutes to just ask question, and I hope that it was interesting, and let's see if you have any question that I might help you. So I was a very good presenter. If you don't have any question, here you are, guys. Okay, so green shape is the word that I used to explain you when we take a powder, we fill the mold inside during compression mode, we fill the mold, we compress the powder. After that, we do have to remove the compressed powder and place it in the oven. This compressed powder has no strength. If the compacted powder falls on the floor, it breaks in powder again. So I call it green shape. Is just a compacted powder with no long-term bonding. They are just particles bonded together. Just to make you an example, it can be like when our kids are making sand castle, they add some water into the sand and they compact it. That's a green shape. You can move it, but it's quite fragile. If after that we place it in the oven, we will have long-term, long-chain strength that's normal PTFE that we all are used to see in rods or tubes. Ulrich, of course, it's possible for any customer to join the webinars. I guess that you can just share with them the link, and they will be able to register themselves and participate to the webinars. Thank you, guys. I see some one of you that have no question and they are leaving the presentation. I was really happy to present this first webinar, and I hope that you will be back for the next one. The next one, I guess, it will be on materials. So we will see we will see some of PTFE features itself, compounding, so differences between virgin PTFE, modified PTFE, compounded powders. So it will be really, really, really interesting for you guys. Thank you all. I am happy about this, and I wish you a very end of week and a better weekend. Ciao, everyone. Thank you.